Good day, students. Today we're going to look at a solution to another in the series of hypothesis testing. So let's get right to it. The manufacturer of a mobile phone wanted to know if a price reduction of 10% would increase their sales. For 1 month they sold at the reduced price at 8 different locations and sold at the regular price at 7 other retail outlets. The number of sold units for that 1 month are recorded in the table below. At the 0.01 level of significance, can the manufacturer conclude that the price reduction resulted in an increase in sales? Okay, so basically what this table is telling us is that store 1 sold 128 units at the reduced price in 1 month. Store 2 sold 134 units, or mobile phones, at the reduced price, right? So these are the number of mobile phones sold. In the first row is the reduced price, and the second row is the regular price. Okay, so we do have 2 samples here. We have a reduced, okay, and a regular. Okay, and in this particular one, we don't know a lot of information yet, do we? We do know that the number of people in the reduced is 8 stores, and in 2 has 7, right? We don't know the mean, and we don't know the standard deviation of each one, so we don't know these values. However, now we could go to the calculator, put these, for example, in list 1 and find the mean and standard deviation. We could do it for the other one as well. However, we're going to use the data function on the calculator and let the calculator do it all in one step. Okay. Alright, so we don't know this information, and we're going to let the calculator do it for us. Now, so let's go through our 5 steps that we use in doing hypothesis testing. The first thing we're going to do is talk about the null and alternate hypothesis. Now, if I look at the question, it's wondering, is it resulted in an increase in sales? So therefore I'm going to refer to these as what? The mean of this one I'll call mu1, the mean of the regular price mu2. Now, so it's asking us, has the reduced price increased the sales over the regular price? So is mu1 greater than mu2? Of course, the null hypothesis would be mu1 less than or equal to mu2. And again, remember that the equal sign is always contained in the null hypothesis, and the null hypothesis usually is this status quo, no changes. Alright, now alpha is picked for us, 0.01 level of significance, so that's pretty easy. The test, I think you realize it's a t-test we're going to have to use because we do not know sigma, right? Sigma, the standard deviation, is unknown of these populations, and this is mostly the true story. We usually don't know the standard deviation, so this is the most frequent test, right? And if you look at the sample sizes, they're quite small. They're both under 30, so that would verify a t-test for sure. Now you notice down here the chart I have this time is slightly, below normal. In other words, it's a sort of smaller and flatter, where normal would go up higher a little bit usually, right? And so on. And that's because the t-distribution with small numbers is usually a flatter distribution, spread out a little bit more as well. As numbers get higher, the t-distribution becomes closer to the standard normal z-distribution. Now, let's look at next step, step 4. That's our decision rule. What is our decision going to be? Well, in step 4, there's always a little bit of work to do. It's an inverse t function, and for inverse t we need area and degrees of freedom. Okay, how do we get both of those? Well, degrees of the area we'll do first. As you can see from our alternate hypothesis, greater than, so we call that a right-tailed test. Okay, right-tailed. And because it's right-tailed, I know the area is going to be 1 minus alpha, right? Because we want the area up here, right? And remember, the calculator goes from here up. So in order to get that, we have to use 1 minus alpha. Okay? So it's going to be inverse t of 1 minus alpha, and degrees of freedom. Now degrees of freedom, again, this depends on when you're doing 2 sample t if the data is pooled or not. Now what do we mean by pooling the data? Pooling the data means that if we can make the assumption that the standard deviations of both are the same or equal or near equal, then we can pool the data and use a 1 statistic versus using 2 statistics. So in this case we can assume that they're equal, and we will assume, and therefore the degrees of freedom is n1 plus n2 minus 2, which of course is 8 plus 7 minus 2, or 13. 15 minus 2. So the degrees of freedom here is 13, and 1 minus alpha, let's write it down one more time. 1 minus alpha would be 1 minus 0.01, which is 0.99 and 13. Okay, so looking that value up, second function, go to distribution, so second vars, go down to number 4, inverse t. The area is 0.99, and degrees of freedom are 13. And again, degrees of freedom, we're making the assumption that when we're pooling the data, in other words, that our standard deviations or variances are the same. So 2.65. Alright, so 2.65. Now, so up here somewhere at 2.65, and it's just a sketch. It's not an accurate. Okay, in other words, this little area in here, okay, right, which is 0.05, oh sorry, 0.01, right, and this is going to be our reject region, isn't it? So anything greater than 2.65, we're going to reject the null hypothesis. So there's our decision rule. So if the test value we get in, okay, now I have 2 different t's here, so I'm going to call this one TCV, critical value, right? Because we often refer to that as a critical value. So if the test value we get, the calculated value, is greater than 2.65, then we are going to reject the null hypothesis. Okay? Number 5. Now step 5 requires us to do some work as well, and how do we draw that conclusion? Well, you notice here we still don't have that mean or standard deviation of the populations, but what I did is I've already taken the information and put it in the lists. Okay, so go to your calculator, clear, now stat, okay, go to edit when you want to enter anything in lists. Now notice I've already put the data in. So these numbers here, 128 up to 120, are in list 1, and I have the others put in list 2. Okay, so I've entered the data already. So if you want to pause the video and put the data in your calculator to double check everything, go ahead and do it at this time. Now, so I've already put the data in list 1 and list 2. So now we go back to stat. This time we'll do our test. We're going across to our test. We're going to 2 sample t, but this time I'm going to use the data. Because I have the raw data, I'm going to use that. So I make sure you highlight data, not stats. We don't have the statistics. We don't have these 2. We don't have these 2 as well. So we're going to have the calculator do the test from the raw data. Now watch what happens when you hit enter now. It's asking you where the data is. Look, list 1, right? In other words, this got to be the first one in this series, so it had to be in order. So it had to be this group here. This has to be in list 1, right? Which is N1. I have, so in other words, mu1 is in list 1. Mu2 is in list 2, which I have done. Frequency 1 and 2, yes, keep them the same. Keep them as 1. Now it's a right-tailed test, so you should have greater than highlighted, which it is. So let's go down, and You should have pooled data. Yes, we're assuming the standard deviations of the samples are the same. Therefore, we're pooling our data together. And then calculate. Let's see what we get. Now notice it will give you the mean of each group. Right there, look, x1, x bar 1 is 125. So if you want to write those down, you don't have to. But if we had done it separately, we would have got this for the mean of the first one. The mean of the second one is 117.714. And if we go down further, we can get the standard deviation of the first one, 15.094, and the standard deviation of the second one, 19.914. Now you don't have to jot those down, but just to show you that those values were calculated as well. Let's go back and look at our t-value. The t-value is 0.81, I'll round it off, 0.819. So the actual t, and this is the test value if you want, or calculated value, is 0.819. Now, is that greater than 2.65? No, it is not. It's not, right? It's found in this region, which we say is the accept or do not reject region, right? So 0.819 is somewhere around here, right? 0.819. So it's in the accept or do not reject. Some people say it the other way, do not reject. Technically you should say it as do not reject, but we'll just say accept HO for our purposes. And the t-test here is done. Now what's our conclusion? Well, it's in the reject region, isn't it? Or accept region. So we're going to say do not reject or accept HO. Okay? And you should write that conclusion out in words. Now, what does that mean? Well, remember what the question asked. It was asked, did the price reduction increase its sales? And of course, the alternate hypothesis is no, it doesn't. It doesn't affect the sales. And that's what we accepted. So if you had to write this out in words, you would write something like that. The price reduction did not increase sales, or something like in that effect, right? So the price reduction. Now we can say that with, we can't say it with all certainty, but we could say it with some level of confidence that the price reduction did not increase sales. Okay, so write your conclusion out in words, something like that. Now, just before we close off, I want to bring your attention to the p-value. Okay, the p-value here, which is an extra test, turns out to be 0.214, rounding off. That's definitely greater than 0.01, which is alpha. And when p is greater than alpha, we learn to accept, alright, the null hypothesis. So there's another verification that our t-test is correct as well. And this is extra. Okay? So there's another example of hypothesis testing. That's two sample t-test using the raw data button on your calculator. Alright, that's it for now. Over and out.